Cool, thank you. I'm Martin, Solutions Engineer at SurrealDB. Happy to be here. Welcome everybody. A lot of familiar faces again. Nice to see. And yeah, not sure if this is a show, but hopefully it will be entertaining or yeah, so you come back. But first, SurrealDB, and then let's speak about knowledge graphs. SurrealDB is an open source database. It started maybe already 3 years ago, became public in GitHub, and then started trending in the Rust communities. There were a couple of YouTube videos back then. They got me engaged. I started using SurrealDB again like 3 years ago when it was still in beta, and I hadn't stopped since. And SurrealDB has continued growing, offering new products. You can self-host, but then we also offer the SurrealDB cloud there. We now have a lot of the security compliance things in place, and we are used by a lot of big enterprises as well around the world that we know of. Maybe there are a couple of stealth enterprise POCs being built there that we don't even know. And usually we then realize, oh, they're using SurrealDB in Walmart around the globe, embedded in vending machines and things like that. That happens because of some of our nice features. SurrealDB is built in Rust, so it's a very efficient and small binary that runs almost everywhere. It runs in the browser, so you can embed SurrealDB in a browser for demo purposes or for real data analytics, like on-prem, on client side. Or you can deploy it in high available multi-node architectures for high availability and scalability and everything. So it's very powerful in that way. It's very common now for AI because it's multimodal, and turns out for AI that's a great feature to have documents, relations, vector store, and graph relationships and everything in the same database. So you can have a single query touching graphs and vector stores and doing hybrid search, even with full text search and whatnot. It's not SQL, it's SQL-like. So it's easier to understand how you relate data because we don't use joins, we just use dot notation. So it's much simpler, more intuitive to join data from different tables. And we also can have things that SQL doesn't have, like graph queries in the same language, plus custom functions and a lot of nice things that you can add in the query language. As I mentioned, it's multimodal, so this is almost, or if not all, the modalities we have in the database. We have geospatial, time series, vector search, full text search, and everything you can basically put in a key value store as well. And yeah, that's SurrealDB. I have our app that I will show in a moment, but for now let's start with knowledge graph. Does everybody know what a knowledge graph is? Yeah? No? Okay, cool. Because I have the explanation from Wikipedia. And I think it's the best one because it doesn't mention AI. And I wanted to reinforce this because people now use a lot of words they think are related to AI where they're actually not. So it's important to understand what a knowledge graph is first before just thinking that's a solution for AI and it's a solution for everything. But it's basically connecting entities with graph edges, in this case relationships. So there's a lot of things in the world represented by graphs. You have a lot of concepts that are related by different ways. Knowledge graphs became very popular like a couple of decades ago. And one of the big use cases was search engines, for example. Google uses knowledge graphs to understand the relationship between different concepts and then provide better search results. And in a way, that's why we use knowledge graphs for AI nowadays, just to have a very powerful search engine for agents, so that we find the best context that an LLM requires to then generate an answer. They look something like this. This is a very simple, of course, and even zoomed in graph that's also very explicit. So if you have even a transactional database, let's say an e-commerce, it's very easy to extract from that the products, the reviews that users have written for those products, categories assigned to those products, and even orders where that product was included and so on. So it's a graph based on very explicit data with very explicit relationships. So it's a very explicit graph as well. On the other hand, there's different graphs that can be more like inferred, where the relationships are not as easy to guess. And sometimes you need an LLM to actually infer those relationships or even infer the nodes. So sometimes you infer keywords from a chunk, and then you have to infer the relationship between different keywords or concepts and users and different entities. In this case, this is actually more like a hybrid graph, because some relationships you could see there are very explicit and some may have been like inferred as well. So for example here, for the ones that are not as close, we have, imagine we are ingesting documents in a knowledge base. So you have a document that was published on a specific year, so that's very explicit in the data. It's also very explicit the author that wrote that paper or article, but then you don't get things as explicit like if there's a concept mentioned on one of those chunks, and if that's related to a company, and is that concept then related to the company as well, and those types of inferences that an LLM may make for you to be able to build this knowledge graph. So again, just contrasting two different use cases, a very explicit one versus not an explicit. But then, why do AI agents require a knowledge graph? Some people maybe are already thinking, what about vector? But basically, it's because agents are very good storytellers. I really like this analogy. So they can, if you ask something and they don't have a clue, probably they will try to answer that. And that's why, that's the difference between ChatGPT and an agent. Usually an agent has some way to retrieve knowledge or context from somewhere based on your own data, your own corpus, ingested documents, chat conversations, support queries, things like that. So basically, this analogy says that an LLM with a knowledge base is then that storyteller that has an encyclopedia and then can do the fact-checking, figure out the right context, and then provide an answer that's not just a story, but something that you can trace back to the actual facts. And what about vector embeddings? For those that may not be so familiarized with vector embeddings, this is a simplified visualization of vector embeddings, but basically vector embeddings are like a numerical representation of concepts that put a concept somewhere in a multi-dimensional space. And things that are very semantically similar, let's say like car, bus, and different transportation methods may be placed close together, and they may form a cluster in that multi-dimensional space. So by having concepts closer to each other, you have more semantic similarity. And when you do vector search, what you're doing is searching things that are close together. So if you like when you use Shazam to listen to a song and figure out which song it is, you can imagine that it's looking for something that sounds similar in a vector space, and then retrieves the closest song to what the audio you send. So it's similarly, but not the same. One thing that you can notice from here, and if you go deep into the theory, actually vector embeddings are, in a way, like an implicit graph as well. But when you have both, you can have those clusters of concepts in the vector space and connect those nodes in a graph. So basically that allows you to trim the whole space and just use those graph nodes to actually trim and focus on the ones that are related to you. So imagine you got to this cluster, but you know you want concepts that are directly connected to a specific company, right? So you can just connect the vector space cluster with that specific company, and then you will remove a lot of noise around because you are mixing both vector and graph. That gives you a lot of efficiency at scale because basically you are reducing the whole vector store to a very small segment using graph. There you go, basically the same, but there's no rule of thumb to decide if you need vector or only graphs, or if you need both or so. And it's definitely not a tool you need just to use always, just in case, because it can become expensive. It may be even producing worse results than just vector, right? It really depends on your use case. But the rule of thumb is that basically if you are ingesting documents, like free-form docs, probably a vector graph, a vector store, sorry, will get you concepts, very similar concepts to your queries, and provide a good context for the LLM. If you need to make decisions, or you need more deterministic answers, then is when people start thinking about graphs, because graphs imply structure in your store. So you can get more deterministic answers by making sure that whatever context you got from a vector store, by just similarity or proximity, you add the graph structure to trim out what's really not relevant for the query. And then gives you also a bit of traceability, right? So you can have like multi-hop queries, and then basically allows you to trace back how your context was generated. Imagine you get a product from your database, but then you can trace back to who bought that product, when, and from what company, and so on, and everything becomes part of the context. Again, depends a lot on your specific use cases. Now into how to build a knowledge graph. We have the famous ETL structure, so here it applies the same. ETL starts by extracting, and you can generalize this process by dividing it in 4. Again, depends on your use case a lot, right? First, you need to parse whatever you are ingesting. You may actually be able to skip this step if you already have structured data, like a transactional database with orders and products and reviews. But sometimes what you have is a PDF that comes with text, images, tables, and then it becomes very, very messy. So you need to actually parse that PDF into some structured data. Sometimes it requires OCR, so computer starts to get hot and starts processing, and takes a long time because probably it's reading images out of the documents, transcribing them, generating captions. There's a lot of things that can happen during parsing. And that's only for PDFs, right? Excel sheets are a different story. Images are a different story. And you can even have PDFs with text that is not selectable. So there's a lot of ways you can parse different documents. Then once you parse documents, you may have megabytes of just a single document, right? And of course, you cannot send that directly to an LLM as context. It means that it needs to be chunked into smaller pieces. And then how do you chunk a big document, right? There's a lot of ways to do that. You can just, after a couple of lines, chunk there and then do a couple of lines more and chunk that. But you may be dividing like very specific topics into 2 different chunks, and then they get isolated, and then your RAG performance starts degrading. So people have figured out better ways to chunk information, and I added a couple here. Recursive is the easiest one. You just find where you can trim, and then you trim, and then you get probably each paragraph or couple of paragraphs chunked. But you can also use structural chunking, which means that if you had a PDF translated into Markdown, it's very easy to divide it into sections. Like you can see the first heading, the H2, like the secondary headings, and then you can decide, let's do a chunk by each like, subsection, right? You can also do semantic chunking, which is using an LLM to actually, a simple LLM, to check for the semantic proximity or similarity from one paragraph to the other. And if they are very similar semantically, you keep them in the same chunk until you get to a paragraph that is completely different meaning from the other. And then you chunk there and then continue chunking. That's a very good one, but more expensive because you're burning tokens for that. Then you have agentic, which is actually use an LLM to just decide where to chunk, which is then using a bigger LLM, much more expensive, but probably is going to produce very good chunks. And there are different ways, again, depending on your use case, you can just get very creative. For example, if you have chats and you are ingesting chats and chunking them, usually chats have a timestamp. So you can also like see when a chat stopped. Let's say it's a customer service or something with a specific customer, and then you can assume that whenever there's a couple of hours of silence, you can chunk the conversation there. That's a very easy and cost-effective way of chunking. Then once you have chunks, usually people embed the chunks to be able to do vector search. And if you're doing graph RAG with vector and graph, then you want to embed things. And embedding is basically generating the numerical representation of the concepts so that you store that in the vector store in SurrealDB and then be able to do semantic search. And then after you get everything, you start extracting the entities and the relationships, which is basically from the chunks you have, you can extract keywords or concepts or whatever you can infer using an LLM or by extracting in a non-LLM way keywords. There are also like lexical ways to extract keywords. And then you can also infer or just explicitly take like relationships between those entities. Again, if you're ingesting a document, probably the entity relationship extraction is going to be inferred, but at least you know the publication year and the authors, and that's not going to be inferred. That's explicit in the PDF. Something that is also very common when you extract the entities is that you have, by definition, relationships between the chunk and the original document. So that's at least generating one type of relationship in the graph. And you can have the chunk with the document, with the author, and so on. Again, only create those nodes and relationships if it's useful for your use case. If nobody cares about those types of relationships when they're querying the agent, then there's no reason to generate those. Then the T in ETL is for transformation. This is basically a time for you to clean up a little bit of the information. Something very, very common is when you start getting duplicate nodes. So at least what I usually do is you uppercase everything so that you don't get things in uppercase and lowercase. And by deduplicating that way, you trim white spaces, make everything uppercase. That's a very easy, cost-effective way. But but they may be like synonyms, right? And things like you can see here in the alignment. This is also a Wikipedia diagram. You see here that you can generate a graph where you have Arnold as a node and you have Schwarzenegger as another node, and there's actually the same node, but probably they got generated like this. So this stage allows you to find those concepts and try to merge them together, so that eventually when you're doing the retrieval, you find Schwarzenegger and you're already connected to the governor of California and so on. How to find these relationships? I think you can get creative as well, but also depends on the costs and if you need to save or not on this. You can, of course, again, embed those nodes, calculate proximities, and find similar concepts using vector space, and then just decide to merge them together. You can have also humans trying to figure out relationships. But again, this depends on how big your data is, how important it is for you to do this, if you need more accuracy versus cost as well. And then also there's a chance here to do the inference and enrichment. For example, if you have a chunk in your knowledge graph, you can generate a summary of the chunk at this point, and then you store the summary. So you have the document, the chunks, concepts, and summaries as well. Some people say it's not a good idea to summarize chunks because then maybe the summary is going to add hallucinations in the context of the LLM that is going to continue hallucinating. But in some other cases, people have found a way to generate summaries that actually work, which is the case of LightRag, for example. It was a very popular paper a couple of months ago where they actually summarize concepts and chunks just to get a lighter, easy way to start navigating the graph. And then DL in ETL, which is loading, now the fun part. This is just a very simplified Python script that shows how you have the triplets, which is a node, a relationship, and a node, and you just insert that, in this case, in SurrealDB. You insert the nodes and then relay the nodes, basically creating that triplet. And this is how one of those actually very small knowledge graphs would look like, which is very dense, very interconnected. I think especially because it may be just one single document, so it's supposed to be very connected. Now let's see it in practice. A very simple, again, use case. So this is from Surrealist, our UI, where you can just design your database schema. This is how it looks. Our tables are schema full or schema less. That's where you see some dotted lines. Those means that the document is not actually required to be strict schema. And you have dotted arrows, which are record references, like a join in SQL, like a foreign key kind of relationship. And then you have the solid arrows, which are actual graph edges. So you can see here, there's a connection between chunks and concepts with a mentions concept edge in between. Oh, and I want to show again, for example, this chunk is embedded, so there's the embeddings array of floats. So here I'm showing you have relationships, you have objects, documents, and graph and vector in the same schema. Now let's see. There's just a video, just so I don't have to do the live demo. This is how it looks in Surrealist, our UI. This is just I was navigating on the graph. Usually, what you do just to like randomly pick a chunk and see how it was generated and have some kind of observability and see what it's doing. I think I also have some queries here that I use the same database to have some stats. So I think this at this moment was like running my ingestion script. So I have some scripts that let me see what's the process, like how many chunks I've chunked, how many concepts I've inferred, and so on. So I'm keeping like the whole process again in the database. Let's go to the next. Yep. Yeah. So now that we created the knowledge graph, then we need to go into retrieving the data, right? So now imagine there's a user with a prompt and you have an agent and you need to build the context for that agent. There is two ways now that we can divide this into. First, we have the traditional RAG. It's actually traditional, probably graph RAG or hybrid RAG, or depending on how many modalities you add. But here is basically where you create a context, you retrieve something from the knowledge graph to give it as a context to the agent, and then the agent generates an answer from it. Then the other new approach is agentic RAG, where you let the LLM find the context by itself with the use of LLM tools. So now modern LLMs can actually like call tools or call functions. So an LLM can actually do a web search for you. And in the same way, an LLM can query something in SurrealDB. So what I usually do is that I create a knowledge graph retrieval tool, and I give that to the LLM, and then the LLM decides if it needs to call this tool to run a query against the database. Sometimes you have also like multi-agent architectures, where probably it becomes a very complex workflow, where an agent is probably just deciding which other agent to call, and then the next agent decides to do a web search or call an MCP, and eventually someone decides, let's try to find something in our own knowledge graph, and then it calls like the custom tool to access the knowledge graph. And then this can just iterate and be recursive, and then eventually return to the user. There's also common to have an agent that kind of calculates how good the answer is, and if it's good enough, it responds, and if not, it just iterates over again. Again, depending on how much money you have, because this can be very expensive if you just enter a loop and burn a lot of tokens. I know this is very small, but just I wanted to show on the left, you can see it's a complex query. It's a single query in SurrealDB. That single query combines vector search with graph queries, and then re-ranks and transposes the arrays into groups and generate a nice answer, and that goes directly to the LLM. And this is probably, again, a bit small, but this is how a custom tool would look like. This is using Pydantic AI. So basically, I am just creating a retrieve tool that is going to be passed down to my agent. And it takes a search query, in this case directly from the prompt of the user. And the agent translates the query slightly to make it searchable, and calls now an internal function to run the query. Right? So this part down here, I have the SurrealQL. Oh, sorry. The SurrealQL is the SurrealQL query from before. This long one on the left. So basically, this retrieval tool is just executing that query, and then the results go directly to the LLM to generate the answer. This is not an LLM generated query. So maybe thinking about that, you can have like predefined queries and then allow the LLM to call those queries, especially if you have a very strict or explicit graph. But sometimes if you have a very like highly inferred graph with a lot of inferred relationships and nodes, you want the LLM to actually generate the query. So to have the LLM do the select asterisk from where and kind of do the graph traversal agentically. If you want to do that, advice, the best way to do that is with few-shot prompting. So you give it a couple of examples, like these are the type of queries you can run, and then the LLM is very good at creating its own new SurrealQL query to just randomly access the graph and do whatever it wants. And this is more on the Pydantic AI side. This is how the agent looks like. It has just simple system prompt or instructions. And actually, yep, the tool is registered before. And then whenever you ask for, in this case, was something about some statutory requirements, and it did the query to find the concepts that are more similar to the query, like in semantic meaning, and then also on the chunks, and did like a hybrid search, combining chunks, concepts with vector search, and then doing the graph traversal to find like the matching or the sibling chunks, and from which document, and then use the document to answer, not only the concept or the chunks. In this case, this again is a very simple graph, but we have that traceability that we know that the answer is coming exactly from a very specific document, right? So if we only had chunks and vector search, we wouldn't be able to know exactly what document is. We will know the chunk. Of course, there are ways to add for each chunk the document, but with the vector relationships, then you can basically trace things back. This is how, when you run the agent, looks like in Logfire. I think we may have a demo about this later on, but this is about like having agents in production, right? Without this, it's very, very difficult. The nice thing about this, if you haven't seen an observability tool like this, is that you can see, in this case with Logfire, like a full stack observability. So you can see when the query is running in the database, but also when the model is choosing tools and the context the model got, and then the answer. So basically you get end-to-end traceability or observability. So I find myself a lot of the times just watching this to see if the agent called the tool I wanted it to use. And if not, then you find your system prompts and then run again and see that, okay, now it actually choose and use the retrieve tool. And then you can click on there and see the search query and eventually the output that the SurrealDB got. So it's, without this, I don't remember how I did this before. And yeah, that's it. Questions before I...
Thanks for your presentation. I have two questions just merged into one. You mentioned about the tools that you used. You mentioned about Retrieval, and I was wondering if you could just elaborate on the tools that you use in your agentic workflow, and how do you evaluate the performance of your agents? Thank you.
Good questions. Well, for the Retrieval tool, this one, it's a custom tool, right? So usually they're in Pydantic AI, different frameworks, and even LLMs themselves have built-in tools that you can find in the documentation. So a very common one is web search or web fetch as well. But this one is a custom tool. So it means you define it and then you pass it to the agent. You have to be careful with the arguments. So in this case, this tool is clear, has a clear description. That's what the LLM reads to decide if it needs to use this tool. And then again with the arguments, the search query, for example, this one says just the search query. The LLM knows that it needs to send there the query. So you can have multiple of these tools with very specific descriptions. so that the LLMs can just pick your tool and run it. Again, depends on your knowledge graph. You may want to have 5 of these retrieval tools to retrieve different parts of the graph, or you may want to have just one that uses as an LLM to write the query for you. So it really depends on your use case, which takes me to your second question, how you know if this is accurate or not, right? I think that's probably the least fun part of doing this, but it's not that complex, but may take time. Basically, imagine a spreadsheet with questions you expect, known answers, and then you basically try to run that. And ideally, you get all possible questions, all acceptable answers. Then you run your agent with all those questions, and then you score them if it's good or not. And you need also to define what is good or what is not, how to score them. And then basically that will give you like a score, overall score. And you can tweak your tools, you can tweak your system prompts, you can even tweak your vector embeddings models and run the whole thing again and see if your score improved or not. But then you need to be wise about it and say, okay, let's have one of those spreadsheets with our called ground truth documents, and let's just randomly pick X amount of questions and then run this LLM or agentic system through only those, and then iterate and go. I think one thing that people sometimes don't realize is that it's about experimenting, which means that you want to repeat your experiment, which is just scientific method. So you need to be prepared from the beginning to make sure that you're not going to get right on the first try. So you're going to iterate over. So everything you're building to be able to iterate quickly or efficiently, then that's great. And the way, for example, I use the same database to store some analytics and some process states and everything, that helps a lot to quickly iterate. Thanks.
Thank you so much. It's a really great talk. I had probably a quick question, which is, you know, the example that you had with the document ID that's passed, is it the graph component that enables that when you were talking about when to go for vector, just vector on its own, or vector and graph? I think with one of the examples you had that you were able to like trace back and get the document ID. Is that the benefit of the graph when you were talking about it being more deterministic and traceable?
Yes, but this is, again, a very simple or maybe very bad example to demonstrate that, because it's very easy to know which document the chunk is related to, right? But sometimes there's a trending article this week or last week about context graphs.
Yes.
And I'm glad everybody read that. Because I don't kind of agree with that article, because context graph is a very generic term for what they were talking about. But what they specifically were talking about is to have things that have like a decision was made because of this, and then that thing is related to something else.
Yeah.
So when you operate on the knowledge graph, which was one of the Wikipedia's definitions, when you operate on the graph, you can also like edit the graph and add those kind of relationships, and then that helps you trace back your like generated answers, especially for law firms, for example, and what else? Yeah.
Nice. And I guess with the observability example you have, you can pass for example, the document ID as a span. So then if you wanted to look at that within whichever observability platform you're using, you can kind of have it as a structured output there. Nice. Okay. Thank you very much.
Yeah. You can add the spans in Logfire, and anything you sometimes people print, you can just send to Logfire. In this case, full stack. So from the queries that go to the database to prints in your code to what the LLM is doing.
Nice.
I was just going back to this definition. I highlighted, it represents and operate on data. So knowledge graphs, sometimes they are very static, but sometimes you can actually edit the knowledge graph, and then basically you can then trace back things you already generated. There is another question.
Yeah.
Okay.
Hi.
Hi.
So I have a question about the retrieval part. So sometimes it's very difficult for LLM to generate the query for the correct when the graph is very complex and it has very specific business use case. So what I felt is like it's very difficult for the LLMs to create the cipher or maybe the surreal queries based on few shot learning. I was also trying this, but are you also thinking in having some kind of a small language model which is specialized to find or to generate these queries rather than using the world models? Or is there any other best practices that you use for generating these queries?
What I've seen working very good is, apart from the few-shot prompting, sometimes you have even more complex graphs that then you need a lot of few-shot prompting, and what they do is, I've seen you have the examples, but then you also can have like counter examples of things what to not try to do. Sometimes it just hallucinates things in the query language, and then also more like specific like guides, like if you want to do this, try this way, and then the example. These system prompts, I've seen some become very, very big, and they are not big from the start, so it means that you kind of iterate over and over and over until you get like consistent good queries generated. I think that's the way. So you basically need to figure out a good way to make sure that you score your results, and then you change something, and hopefully only one thing, and you see if that improved or not the result, and you iterate wisely there. There's a lot of things in prompt engineering. There you can even use genetic algorithms to genetically improve your prompts. But it sounds very nice, very cool, but I'm not sure if that's practical enough. But yeah, so basically, if you can iterate and kind of score your queries and then improve on them, that's the best way. And you even could have like multiple agents and have one that it's very good at just writing the queries. So you have only specific system prompts for that, and then it gives the result to another one. And one thing that's also common is to retry the query. Not sure how effective it is, but that's common. So if it errors out, you get the error from SurrealDB, and then you pass the error with the bad query to the LLM to have the LLM fix the query. And then you try 3 times, and then you fail if it didn't work.
I've got a question regarding change of the relationship over time. So say you will modify the relationship between entities, and then say as time goes by, the relationship has modified in a certain way, we change them. Would you be able to query point in time or establish that temporal movement, travel?
Yes. That question is not implanted, but it's very good because we have time series in place. So we can query like back in time as well. If you want to compare one query today and the same query last week to see if there is like a difference. But also like editing graphs can be very tricky as well. There's a lot of uses for that, but one is if you are building agentic memory and then you want to like update memories, for example, things that change in time, for example, that's a very tricky use case. But yeah, that's one way, using the time series. The other way would be to use nodes and edges to represent time as well. So imagine having a node for each year, and then you basically are using the same graph to represent time in a way, and so that you don't have to how do you say, like delete things from the graph, just keep adding, and then use those relationships to then be able to trim it down. One thing you can also do is you can add properties to the edges themselves. So you can add like decay values to the relationships. So you know that, okay, this relationship is still there, but it's not longer valid because it's, 1 month old, and you only want relationships that are very, very green. So you can add decay values like TLS values to the edges themselves.
Hello, my name is Jonas. I wanted to ask, first of all, I wanted to say I'm very impressed with everything I'm seeing. It's kind of scary how much migration work I think I have ahead of me listening to you guys. So I wanted to ask about deduplication. I'm building something that requires a lot of extracting entities, mapping relationships. I don't know that much about knowledge graphs, but deduplication is paramount. Like, it needs to be as good as possible. Do all the stuff that all of the technologies that you guys offer, is there like some accepted ways to kind of make deduplication easy or reliable?
I think maybe it depends on how cost efficient you want to be, maybe, because if you cannot afford a lot of money in this problem, then you already removed a lot of options from the way, and you end up having to use like lexical algorithms to find similarities. On the other hand, you can have an LLM just try to figure out if two concepts are the same and then merge them together. So you have a big spectrum of things you can do to solve this issue. But then you can also start from the most cost-effective ways, which is even before doing semantic similarity. You could use full text search, for example, to start with, which is built in SurrealDB. So you can just like lexical comparisons and determine if these two words are the same, starting from there and making sure you uppercase everything, trim everything, remove words that are just like prepositions or things like that. So you clean everything as much as possible with a very like programmatic way. Then you can try full text search, similar algorithms, and then you can go into vector search, and then it gets more and more and more expensive. But I think it's a very creative problem to solve. I think it's more about creativity and your type of data, and measuring when you got to the point that you say, okay, this is acceptable now, and stop there, because then it could take an eternity to figure out the best way to do this.
Okay. Sounds like a lot of work, but thank you.
But the fun work.
Yeah, exactly.
Okay, I think we just got time for one more, and we've got one over here, so I'll just pass you over.
Thank you. So my question has two parts. First is, what you describe is kind of like enhancing RAG from like solely vector search into like vector search hybrid with knowledge graph, which is like kind of makes sense. The first question is, do you have any kind of benchmark that not only the memory is reduced but also the accuracy increased? And the second question is about other than RAG, you mentioned the memory as well. So I did some kind of research in the memory a few weeks ago, and there is like a gray area, and we are not sure that like using knowledge graphs is like an over-engineering, or like is it going to be better than only looking at the last 20 messages, or are they going to have a significant impact?
Yep. So the knowledge graphs are not the solution for everything, again, right? And in terms of benchmarks, I think there's a lot of papers. There's a paper about graph RAG, and they say, okay, this is better than just RAG, traditional graph. And then LightRag came, the paper about LightRag, and they were saying, yeah, they get more accurate. And the benchmarks are really good because they are divided into industries. So if you are in law or medical and so on, you can see that actually LightRag is theoretically better in accuracy than just traditional GraphRag. But in practice, people that implement LightRag don't use like the LightRag repo. They just take the concept, adapt that to your own use case, and then you're trying to assume it's going to perform as well as the paper says. But you can only just test your own use case if you have two alternatives. It's possible that you implement hybrid RAG using vector and full text search and graph, and you could get worse results than just a very simple full text search query. So yeah, you need to be careful and kind of benchmark against yourself to have like kind of A/B testing and know that, okay, definitely graph is working for me because I didn't have graph before and just RAG was not enough. Sometimes it could happen the opposite. Maybe you're optimizing for costs or latency, and your GraphRag is doing great, but you want to reduce costs, and maybe you go back to just vector store, and your accuracy is still acceptable, but you lower the costs a lot. So that can also happen. So it's important that you benchmark against yourself, and then know if graph is the solution you're looking for.